right? So in other words, if I just draw block diagrams of a system that features discrete components, Modelica allows me to find out what those how those systems will behave relatively straightforwardly. And so you've seen this screen before, and the last time I showed you how to simulate systems using the block-based part of Modelica. So you'll remember we've seen Modelica in these two different modes. Everything in Modelica has a graphical front and a code at the back. And so right at the beginning, we wrote Modelica code, which allowed us relatively straightforwardly to transcribe from the equations that we wrote down to a very similar notation, and then Modelica handled all the simulation stuff. And later, when we learned about block diagrams, we could do things like taking a source, and we found out that there was this wonderful little magic trove under Modelica in the blocks section. And for those of you who are in the mood to kind of get creative with Modelica, I encourage you to also look at the other options that are available outside of blocks. You'll see that there's a whole lot of stuff for modeling mechanical systems, electrical systems, and so on. But for our purposes, we're going to focus on the block diagram section. So everything in this blocks section is meant to be an iconic representation of the kind of block diagrams that we've been drawing. And so we would drag in something like a source. Let me just get to the sources. And I do apologize for the speed at which this is going. It's not the fastest. It gets faster, like every time you open one of these things during a session, like it caches, so it does get faster. So usually we've been dragging in a step. But a step isn't a great showcase for discrete systems because sampled steps look a lot like, or let's say sampled and held steps look a lot like the original steps. And so I'm going to use a sinusoid as I did in the TUT example so that you can get a more solid feeling for how this works. And so at the very basic level, I can just drag that on there, and like the first thing that we just want to check is I'm going to simulate this now. So let's just set the frequency here. So remember, also you'll remember that there's this Hertz radians per second thing. So if we want something that does a full oscillation in a certain amount of time, we need 1 over that period in Hertz, right? So if we want something with a period of, let's say, 5 seconds, we're going to put 1 over 5 into that box. And you can actually just put something like 1 over 5. It'll do that calculation for you. We'll use the amplitude and so on. So there we've selected that. And I'm going to simulate this. I'm going to select let's say a 20-second simulation time. Remember, it usually has this weird, because it's built mostly for mechanical systems, it thinks a reasonable amount of time to simulate a mechanical system is about a second. Not for most chemical engineering systems. And so if we just simulate that, we're going to get a simple sinusoid. And it's at this point where things become a little bit weird. Because I'm showing you now a plot which is clearly a sampled version of the sinusoid. And it's a thing that happens when we simulate continuous systems and discrete systems at the same time using computers. It's always confusing because you actually don't ever have a truly continuous system. You only have different levels of approximation. And I want you to understand that when we look at a curve like this, the version of this that we're picturing is that Modelica has used a higher order integration routine in an attempt to closely approximate the correct version of this actual equation. And so you shouldn't, even though this is actually a sampled signal, which is only sampled at particular points, don't get confused between the act of attempting to solve a continuous differential equation and the act of simulating a discrete system. Those two things are quite different. and we achieve them in ways that appear to the naked eye to be similar, in the sense that we have a for loop and we iterate through values and we iterate some kind of algorithm. But in the one space, we're trying to approximate a continuous function. And in the other space, we are simply operating a discrete algorithm. So usually what that means is when we are trying to see the difference between these things, we choose the sampling time big enough so that the effect of sampling is clearly visible. And so what we'll do in order to do that is we'll introduce a sampler into this system. Now, also just kind of a little bit of an implementation detail in OpenModelica. OpenModelica does have a sampler. You'll see here, there's a sampler, there's a zero order hold, and notice that it's got a couple of other holds, it's got a couple of other kinds of first order systems, but the cool thing here is that I can kind of connect these things together, and now I'm very closely approximating what my block diagram looks like when I draw it. And let me just sorry, this at this resolution, it's a bit finicky. Right, so there we have, now we have the original sinusoid and we have a sampled version of that sinusoid. The default sampling rate in OpenModelica for all of the sampled stuff is 1 second. Now you can put in a different sampling time. You'll see here you can put in a different sampling period over there. If you don't put anything, it'll be 1. If you put in 1, it'll be 1. I recommend, it is a little bit hard to coordinate these things. So if you're doing this for big systems, what I recommend is that you flip into the code mode and introduce an actual parameter called something like delta t that you can use in all of the blocks, because then you just have that one place to change it. But for now, I'm just going to keep things simple. Now, when I simulate this, the result will be what comes out of that zero order hold is that signal. So now, is everybody following what is happening here? We've taken that continuous signal, we've sampled it at every second, and then we have run that sampled signal through a zero order hold, which is returning it to a continuous signal. Unfortunately, I want to show you that this happens, but I want to warn you about this at the same time. If I just output, like the sampler itself has an output, which appears to be zero order held by itself, which from an implementation point of view, remember what I said, that zero order hold is kind of the default behavior of how variables works. In other words, if I set a variable equal to a value and I just don't set it again, whenever I look at it, it will be the same value. So kind of every programming language every programming language has a zero order hold kind of just built into the machinery, because that's just like, if you change something, it doesn't usually change by itself. Does that make sense to everybody? So kind of just the default behavior. I strongly recommend, in order to remind yourself that there is actually a separate thing happening there, that you include the hold. But from a, just warning you here, like nothing will break if you don't include the hold. I will subtract marks, and you cannot say, but I built this in OpenModelica and it worked fine, as an excuse, right? Because while from a practical point of view, leaving out the sampler will give you exactly the same signals if it's a zero order, if you're trying to zero order hold. From a conceptual point of view, you've left out a whole component of the actual mechanics of the system. You've left out the fact that a hold element is necessary to interface a discrete system with a continuous one. And so you've made a conceptual error. It doesn't actually result in different values, which is why I'm signposting it really strongly here, because it's easy to imagine that if it works, it has to be right. And I'm just explaining why it works in this one kind of weird edge case, and why it is conceptually wrong and will lead you to lose marks if you leave out the hold element. So basically, you can never have a continuous system interacting with discrete systems without a sampler from the input side and without a hold element from the output side. That's just the rules, right? To get from continuous to discrete, you need a sampler. To get from discrete to continuous, you need some reconstruction machinery, typically a zero-order hold in our case. But obviously there are different kinds of reconstructions. Okay, so hopefully it will now become clear when you see what I'm going to do next. Hopefully things will become a little bit more clear about the example that I showed yesterday, or the case that I showed yesterday when I said, what would a continuous system, how would that continuous system behave if I put a sample and hold in front of it? And so let me just sketch out I'm going to add 2 blocks onto this system. So I'm going to take that original sign and I'm going to chuck that original sign through a first order system. So there's my first order. Right, so that's first order 1. Okay, I'm going to call that first order 1 is fine. I'm going to keep the gain 1, time constant 1, just keep things really super simple. Okay, and if I simulate that, now I'm just going to copy that as well. So I'm going to take the first order, and I'm going to connect that up to the original unsampled sinusoid, right? And I'm going to take the second first order and I'm going to connect that up to the version of that sinusoid that's been sampled and held. Now you can see just from looking at that diagram that I'm expecting different results. Okay? So when I simulate this, let me just plot the stuff that's coming out. I'm going to ignore the stuff that's coming out of the hold. And I'm just going to plot the stuff that's coming out of the first, well actually, let me plot the original sign. So the original sign is there. And when I plot the response of the continuous first order system to that continuous sign, I get exactly what I expect. I get a little bit of transient behavior followed by basically a nice persistent sinusoid. Nice and smooth. Persistent sinusoid. Now remember that the second first order is actually being exposed to a sampled version of that. And so when you look at what that result is, that green line is now the output of that system to the sampled and held sinusoid. Which maybe is, again, if I maybe actually put in that sampled and held version, let me hide these others, then you can maybe see more clearly. So, in other words, what we're seeing is really the first order system responding to effectively steps that are happening every second. Right? So that first response is simply a straight up step response, going from 0 and going up, and if the period were longer, we would actually see it go all the way up into that and kind of reach that sampled value. And then when the next sampled value happens, it'll go down and reach the next sampled value. So it's doing a normal first order response to steps. It's just lots of steps, one after the other. And hopefully this shows you, just even like without doing the math, what these differences are that I'm talking about. Now, this is what I drew yesterday This is the picture that I was trying to draw yesterday when I drew this. Okay? When I said this is what is in, this is the Z transform that's in table 17.1 is I've now got an input signal that's coming in. It's being sampled, held, sent through a continuous system. And the only thing that I haven't done now in the OpenModelica is I haven't actually then sampled that signal again. Right? So I can go and do that. So I can do another sampler. And another hold. So now I have a system that is discrete at its edges. In other words, from the input into that system, so the input into that system, which is this system in the box, has a sampler and a hold element connected to a continuous, which is now first order 2, right? It's then again sampled, and I'm holding it again just so that I can show you that stair-step output, okay? And so what's coming out of that second hold is that. And if I hide the continuous parts, basically that relationship between the sampled input and the sampled output of that particular system is what, that is now a discrete system, right? Because it's the relationship, it's the discrete relationship between a sampled signal and another sampled signal. The two sampled signals are the sampled signal that goes in there and the sampled signal that goes in there. And I can reasonably ask, what is the equivalent discrete system to this thing that is inside of this box, right? Because I know that there's some relationship that relates this discrete signal to that discrete signal. And if I can untease the input and output in that equation, I can write that as a transfer function. Table 17.1 contains the answer to that question, right? On the left-hand side of table 17.1 is a whole lot of G's, right? Lots of different G's. And on the right-hand side of table 17.1 is the equivalent G of Z within this configuration. And now I want you to understand that why it is inappropriate to think of this as simply the discrete version of G. It's a very specific answer to a very specific question, right? Given G of S, which is a continuous function, if I were to sample the input signal and hold it and then put that into the actual continuous system and then sample that output, what would the discrete transfer function be? That's the answer that table 17.1 is giving us. It exists in that form because this is such a common question within the context of digital control. If I want to do discrete calculations only, if I want to use only the Z transform to analyze my control systems, which is an obvious thing to do because I couldn't use the pure Laplace transform by itself because the system contains a discrete controller. Right? And because I can't take the controller into the continuous domain, I can then take the system and at least model it in the discrete domain by modeling this effect, because that's actually the part that I'm interested in. From the controller's point of view, it's always going to interact with the sampled version of the output of the system. And so from the controller's point of view, it can, because remember, the controller is asleep between sampling times. So it's only wondering, like, if I do this, what will the system do in the next sampling period? Right? It's not wondering what will the system do between sampling period because discrete controllers literally can't think between the sampling periods. Has this clarified this situation a little bit? Okay, and so I'm not going to take the time to do that today. But I think it does have, if you want to maybe redo that tutorial, I just want to check the time, because I've got another thing that I want to show you. This approach, I would like to encourage you to take a little bit of time this weekend and maybe go back to the tutorial from Tuesday and build that diagram out and ask yourself, okay, so if I build that sinusoid in Modelica and I sample it and I plot that result, is that the same result that I got using the math in Python? Right? Because that's what we're trying to do. We're trying to say, okay, if we just had these devices, obviously we can just build it like this, okay, but what if we wanted to do math about it? What if we wanted to know, for instance, that a particular control configuration leads to instability in the system? We wouldn't be able to do that math if we only had the simulation. And unfortunately, sadly, there is no direct link. There's no way to take a Modelica diagram like this and get out a Z transform. So it doesn't link in that way. You have to kind of do a lot of the Z transform math yourself. And I'm also the bearer of sad news. I have again taken time, every year I do this, and every year I'm disappointed to report that currently there is no similarly straightforward way to calculate the Z transform of a continuous function as there is to calculate the Laplace transform of a continuous function. Right, so like the easy story for Laplace transforms was, yes, there's the data sheet, but in practice you're never going to use the data sheet because you're just going to use Laplace transform in SymPy. And I wish I could tell you, oh yeah, actually tbcontrol.z transform, you just use the same thing and it does the same thing, but it doesn't because I don't know how to write that function. And so unfortunately, this is like a little place where the only way that I know how to obtain the results in the datasheet table is to use the datasheet table. Or a similar table. You know, there are other ones on Wikipedia or wherever. Our tools currently, the ones that we use in this module, are not powerful enough to completely automatically go from every possible input signal to a equivalent Z transform. And so when you put in systems here, so because now this is there's another question which we can now start teasing apart. So we've explored this idea that there's the sinusoid, there's the sampled version of the sinusoid, and we could write a Z transform for this signal. We did that, right? That we can just get straight from the table. Okay. We can also get the Z transform over here, or the Z version of that whole signal going from the sinusoid all the way through, by using the table, because we can calculate each one of these responses and then convert that to steps and kind of have an infinite sum going from there. You can do that analytically to get in between. I don't expect you to do that analytically in this module. We'll do that in the next module. And so for my purposes, the only things that I want you to be able to do in this module with regards to the Z transform are these 4 problems that I spoke about yesterday. I noticed now that I didn't label the 4th one, but there are 4 of them. I'm also sorry, I've been a bit lax with the recording, well, with the editing. I'm trying to edit these down into smaller digestible chunks rather than just one massive lecture on discrete systems. But these are the problems that I expect you to be able to do in the exam. In other words, I expect you to be able to find Z transforms of these exact systems, right? I expect you to be familiar with the backward difference approximation, and I expect you to understand what table 17.1 means, like how those things happen and how to use them. I don't expect you to be able to do feedback loop calculations, so you'll notice that the reading for the discrete stops before we start talking about controllers, and that's perfectly fine. We'll only really be doing controllers next semester. You'll read ahead a little bit to get to the backward difference approximation, because the context of that in the textbook is the PID controller. You don't even need to know what a PID controller is for this module. But it is useful to know that something called the backward difference approximation exists and kind of how that works. Right, so while I'm working on kind of just the mechanics of how to do things, as I've mentioned before, I'm regretting that I've perhaps spent a lot more time in these notebooks kind of explaining how things work instead of explaining how to work things. And so I've extended the Z transform notebook a little bit to also include references to using the control library, and I want to give some guidance about when to use what tools. Now the advice is similar. When you have unknown coefficients or symbolic coefficients, use SymPy. If you have known coefficients, don't use SymPy. It's basically as simple as that. If you have known coefficients, in other words, if you know what the parameters, if I tell you it's a sinusoid with an amplitude of 5 and a frequency of 10, right? when I give you numbers, that's like the sign that you don't use SymPy. If I give you symbols, that's the sign that you should use SymPy. I expect you to be familiar with both, but in my mind, when you are working with numeric problems, the numeric-based tools are easier, basically in every way. And so if you're trying to get graphs, you should be using the numeric tools. But if you're trying to understand the relationships between things, or if you want to see like how the time constant, for instance, affects something, and you want to kind of carry that through in the calculations, there's no way to do that using the numeric tools. And so I just want to again signpost this idea that these libraries do not know about one another. So there's no simple and direct way to take an expression in SymPy, which you with your eyes would pass as a transfer function. So if you look at that and you're like, oh, I can see that is a discrete transfer function. Why can I not, like, why isn't there some function that just like makes a control, well, why can't I just do DL-sim on this object? And the answer is that those libraries, like those authors don't even talk to each other. They don't know each other, they live in completely different worlds, they're not coordinating their actions. And so there's no special attempt to make sure that like .subs does the same thing on a control transfer function object than it does in an expression. And the less you allow yourself to think of these things as being like these magical transfer function objects, and the more you remind yourself that, oh, this is just a symbolic expression object, and these things are control transfer objects that do specific things, the more success you'll have, because then you'll kind of remind yourself, oh, I have to kind of move from the one to the other. You'll see in this notebook, I've allowed myself to just crib these things directly from the textbook's coefficient list. So this A1 and B1, that comes directly from the textbook. Remember, you'll have the textbook available during the exam. So like if you want to know how those relationships work, you just use the textbook version. I do expect you to be able to discretize continuous equations. So if I give you something that used to be a continuous equation, I expect you to be able to kind of work through the math to figure out what the new coefficients would be. SymPy is useful there, but as always, if you're super good with algebra, you maybe don't really need SymPy. Me personally, I suck at algebra, so I need SymPy for even basic math. And so I use it extensively, but I also type really fast and I've got a good memory for functions, so it's a trade-off. So, also there's a lot of people thinking like, why do I show you SciPy as well as control? The control stuff is typically a lot better, but SciPy is useful because it's much more universally available. So control, by and large, you'd have to install separately. If you just arrive at some employer, if you just install Anaconda, you have SciPy. You don't have control. And so it's useful to know kind of the lower level tools and what they do. Most of the control stuff calls back to these lower level tools anyway. So again, if you have control available, what I recommend is for numeric stuff, if you have control available, just use the control library. I've learned a really nice trick with regards to the control library, which is this. It's going to be in the notebook when I upload it. Basically, a common point of contention is the idea that you'll see that the control library uses positive powers for Z when it displays and accepts transfer functions. But most of the tables of known Z transforms favor the negative powers of Z, just because it's mathematically prettier. And it's always a bit of a mission. It's not super hard, but like you get confused with the leading zeros. That's always where trouble starts. So manual conversion from the negative form to the positive form is problematic. The two tools that you use, the places where you want to give coefficients of transfer functions like these. So in other words, when you're using Python, both SciPy and the control library expect positive powers of Z, and OpenModelica expect positive powers of Z. And so you have this problem, like how do I go from the textbook or from tables into these? And the easiest way that I've found is to have this definition. You simply create a variable called Z. And what that is just Z over 1. And why that's useful is that allows me to type it allows me to type things like this. So here is the definition of the unit step that I've just directly transcribed from the textbook. So I've used, and I think a lot of you have kind of practiced this skill very, very well, which is kind of just looking at a formula in a book and transcribing that into Python notation. And so this is a relatively natural way. You don't have to worry about like identifying the coefficients. It will automatically insert 0 coefficients if they are there. It will automatically convert these from the negative z's to the positive z's. And by the time that you're done, it will basically do that. And so you type this, right, which is what's in the table, but what you see is this, which is what the thing actually needs. And you basically save a conversion step. So it means that it's easier for you to check that you've done the right thing. I recommend that you do this even if you're doing something in OpenModelica, because there's no equivalent way of doing this. So you can just use this trick to get the positive coefficient version and then type that into OpenModelica and be done. So that's my recommendation if you just want to get stuff done. I also want to show you that if we have a transfer function, there's G. So continuous transfer functions, where's my continuous transfer function? So that's a continuous transfer function in S. The control library features a method on these things called sample, which allows you to do approximations using sampling on that transfer function. And effectively, that automates the process of doing a backward difference substitution. There's a couple of different techniques. The only one that I want you to really know of is the backward difference one. That's the one that we discussed earlier. And basically what that means is you do dot sample and you pass a sampling time. So let's say a sampling time of 1. And then you have a method. Now the zero order hold method is the one that I just discussed. That's where I've got a sampler and a zero order hold in front of the thing. And so I'll leave it as an exercise to the reader to confirm that that is the correct result if you use the zero order hold, if you look it up in the table. And if you do this, you get a different one. Sorry. Is it a dash or is it backward diff? There you go. And so you can see that those results are numerically different. And so obviously at least you can see that they are not like you're getting a different answer because you're asking a different question, right? So keep in mind, just like the tutorial, it's maybe useful to kind of also just compare this with the tutorial results. I find it very useful to do these kinds of simulations to make sure that like when I say, oh, I think that this should be this, how do I check that I've done the right thing? And I want to kind of just end this lecture, the part about the discrete, with that idea is in each of these cases, it's important to know how to check that you've done the right thing in a way that doesn't involve like looking at the answer that somebody else has made. But like if I have done my job right, if I find the Z transform of a signal, this is relatively straightforward because if I invert that Z transform, in other words, if I get the values at the sampling intervals using one of the techniques that you now know quite well, I can just plot those dots, right? So I can just these sampled values should correspond exactly. So if I've done my job right, if I do that plot, at every sampling point, I should have just exactly the values of the sampling point itself. And so if I sample a signal and I think I have some Z, like some nice closed form Z transform representation, if I expand that Z transform into coefficients, and I look at the coefficients and I plot those values over the original function, they should be 100% on top of one another. Like 100%, no error, no slight shift, no one-time step shift, which is a very common error when you're working with Z transforms. Nothing like that. They should be like an exact match. For the Z transform of a discrete system, you can do something similar, but it's useful then to kind of implement the discrete system using logic. Usually it's easier to write code to do a discrete transfer function. So if you say something like, if the difference equation is something like yk is equal to a times yk minus 1 plus buk, now that implies a for loop that says for y is equal to a times y plus u. If you want to do that k. So remember that in the normal state of things, every time I go around a loop, that y would be the previous version of the y on the right-hand side. And so that difference equation implies a formula. If you're not that cool with coding, you can also write the same thing in Excel. And again, now you're looking whether you're getting the same values. The Z transform of the system subjected to some input should give you the same as if you had actually worked it out using Excel or Python. And that's how you check yourself, right? Like you do the calculation using the Z transform. Again, you invert that final Z transform result to get the values at the sampling points, and then you simulate it in a different way. You do it in OpenModelica, you build the thing in Excel, you write the for loop in Python, you do one of those things, and those values should 100% match up, okay? When you are doing these approximations, there isn't an equivalent check to know that you've got the correct function, but you can at least check that it is reasonable. So here you're expecting the functions not to lie on top of one another, but to lie near one another. So with the backward difference approximation, you're expecting to get some similar behavior, but you know that you're introducing at least one time step of lag, and you're introducing maybe small errors in how the system actually operates. Remember, it's impossible to approximate a continuous system with a discrete one without introducing at least one time step of lag, because I always have to do at least one calculation, and that one calculation can never take 0 time, right? Like I'm always asking like, so what's your value for the next time step? And then I'm like doing whatever calculation, even if that calculation takes fractions of a second and the full time step is a full second, the calculation is only available at the end of the sampling period because it can't report the result earlier than that, because fundamentally it can only report the results at the sampling periods, and it can't report the result immediately. So it always has to report it one time step late. And so when you plot these results, you expect them to be at least one time step shifted, maybe more, depending on the width of the algorithm, right? And then lastly, over here, this one is also relatively straightforward. Here you should be able to get, again, an exact result, because if you simulate the system, in other words, if you take a continuous output, like that continuous sinusoid, you sample it, you hold it, and you put it into that continuous system. You can use OpenModelica for that, or you can do it analytically. When you then plot those signals, they should line up 100%. And so there's only one place where we're making an approximation error, and that is when we are doing approximation. Right, so and that's this point number 3 type, which is if I wanted to find like an equivalent or an approximate equivalent GZ, what would that be?